Hi everyone, this is Dattaraj Rao from Persistent, and I'll be talking about our paper Zero Shot Learning Approach to Adaptive Cybersecurity using Explainable AI. This is joint work between me and Shraddha Mane from our team. Shraddha is a data scientist, and I lead the AI research lab here at Persistent. So what we are proposing is a novel adaptive approach to cybersecurity, and the reason for this, as we see in today's news headlines, there are a lot of cyber attacks happening. Cybercrime is on the rise, especially with the COVID situation. Ransomwares and different types of attacks are happening, and these are very novel. They try to exploit vulnerabilities of the system which we are not aware of. Zero-day attacks, so it is important for us to understand that the attack can come from anywhere. They can exploit any vulnerability that we have. So our cybersecurity systems need to be adaptive to these attacks. Need to quickly figure out that the attack is happening and alert our operators. Learn from the cybersecurity analysts and adapt to automatically start detecting those attacks and distribute this knowledge. So an adaptive cybersecurity solution is the need for the day, and our paper talks about one idea that can help us drive in that direction. Our idea basically is we want to look at an anomaly detection system, but enhance it using zero-shot learning. Like we have the anomaly detection that can say, okay, this is anomalous, and this is normal. But we want to take it a step further, where we want to auto-assign labels using zero-shot learning, so that when we show the cybersecurity analyst the alerts, we don't just show it as a black and white alert or not alert, or anomaly or not anomaly. We also want to provide some supporting evidence and some intuition from explainable AI, such that the cybersecurity analyst, can take an informed decision of what playbook to use to handle that particular attack. So the way we see this system in production is as live network data comes in, our anomaly detection model works on this data. We, in this particular example that I'll show, and all the code that we have developed is available as a Colab notebook on Google Colab. So it's 100% reproducible. You can directly, without having to download anything, log on to Google Colab with your account and run the code and reproduce these results. So what we are looking at is an anomaly detection model. In our case, we use isolation forest algorithm for it. We trained it on NSL KDD dataset because NSL KDD really has some good label data, and we could correlate the anomaly label to the features. And then we have a model explainer, which we use SHAP to leverage the model explainer on the isolation forest, and then use that to train a zero-shot learner. So the way we see the system is, once the anomaly is detected, we figure out if it is a known anomaly. If yes, we directly show it to the analyst, and the analyst ideally has predefined playbooks to handle that anomaly. If it is not a known anomaly, we pass it to a zero-shot learner and try to auto-assign labels using a combination of features based on the importance. And that information is fed to the analyst, so that along with the unknown anomaly type, the analyst is also given some information on the importance of features and maybe some correlation to previous anomalies based on the feature importances. And that will help the analyst understand which sort of playbook will be better to take action against this anomaly. So that's in a nutshell how our system is intended to work. The example that we did was using NSL KDD, and the NSL KDD, most of you will be aware, is pretty much a network intrusion detection system dataset. It has different features like protocol type, services, flag, etc. And the labels are the anomaly names. So here are the top categories for the anomaly names. It could be normal when no anomaly, or different types of anomalies like Neptune, Saturn, IP sweep, and this tells you this is a suite-wise analysis, tells you how the distribution of anomalies is. So we trained an isolation forest algorithm, which basically just tries to find if it is a normal or an anomaly, and we had to do some feature engineering for that. But once the model is trained, we get a pretty good precision and a recall in the 90% range. Now we'll use that anomaly detection algorithm, isolation forest, and we trained a SHAP explainer on it. And that explainer will, first of all, it will assign a SHAP score to each entry, each data point, and we'll be able to aggregate and get like a feature importance plot telling which features are more important. But now this is not what we'll directly use. What we will use is for a particular type of anomaly, if we can distinguish that anomaly based on the shape values, distribution of shape values. So that is the core thing we want to do, is looking at the type of anomaly, if we can distinguish which features are important and the pattern of how the anomaly is explained, and use that to classify, auto label the anomaly and give additional insights to our cybersecurity analyst. An alternate way also we look at is using Lime, which is a local explainer, where we kind of form these rules. So this was one of the first things that we did. Once the anomaly is classified as an anomaly and we get explanations, can we do a Lime explainer and kind of extract rules out of it? So this is something we can provide to the analyst also, that okay, we flag something as an anomaly, we don't know what it is, but this is why we flag it as an anomaly, because service and NNTP is so and so, because wrong fragment and things like that. So can we kind of give an intuitive rule, and maybe using some models generate a human language saying this is why we have classified this particular data point as an attack, and maybe that's intuitive to the cybersecurity analyst. The other thing we did was using the SHAP scores that I showed earlier. We tried to classify. We took certain points which are normal, certain points which have guest password anomaly, port sweep, and wedge master, and based on that, we tried to see the pattern of how the explanations are. And this is a nice SHAP force plot which shows you what is the pattern of the explanations. Now, looking at the pattern of these explanations, we can clearly see that there is a distinct difference between how port sweep is explained and how Westmaster is explained and how guest password is explained compared to the normal. Now, if we know this knowledge, we can kind of, next time we see something similar to a port sweep, even though it is not classified as a known anomaly, we could directly map it to something similar and give that information to the security analyst. So what the way we envision the system working is, we have like a lookup table where for that particular for each anomaly, we can try to map it to an existing anomaly, or map it as a totally new anomaly and give either the rule that defines the anomaly or some sort of an explanation of top features, and get feedback, solicit feedback from the domain security expert, cybersecurity expert, that this looks like this particular type of anomaly. I want to name it something. And now the system is adaptive. It learns from the cybersecurity expert and stores that. So next time a similar anomaly comes with that explanations, it will automatically try to classify it. So that is the adaptive nature of the system that we are proposing, and using zero-shot approach and cybersecurity and explainable AI, we see that this can help us enhance our existing predictions and bring in the zero-shot learning capability. So that is in a nutshell the work that Shraddha and me had looked at. And this is like I said, all the code is available on Google Colab. I have provided the link in the paper. So look forward to any feedback from you. Thank you.